So welcome everyone to the future of architecture. In fact, the first talk of the future of architecture. And here it's hosted by myself, Akil. I'll call myself the host. And today we'll be talking to our guest, Timo. And Timo is a computational designer. And he's going to get a little bit more into himself. In fact, I'm not going to give away too much because Timo expresses it best. Timo is excellent with words. He has an excellent way of carrying himself. So I'm going to allow him to do all of the talking versus me. Just before we start really quickly, I'm Akil from An Architect. An Architect is an independent research and education organization dedicated to making knowledge accessible, not just for architecture, but for fields as a whole. So we firmly believe that architecture could be an umbrella branch for all of the other fields. And so we think that perhaps if we start with architecture, the rest would follow. You see, that's all I'm going to be saying for now. Timo, please take us through an introduction on yourself so that everyone can get more comfortable in this room that we have available to us.
So first of all, thanks a lot for the invitation to come and have a chat with you today. And I must say, I actually feel quite honored to be talking about the future of architecture, given that I am working right now as a structural engineer and computational design specialist. But as you also say in the text you sent out, I try to be a very architect-friendly structural engineer.
Yes.
And it brings me a little bit to you see my background. I did my studies at Technical University of Denmark, where I studied something called architectural engineering, which in this case means that I was taking a structural engineering degree, but at the same time, this course allowed me to do about 20% of my courses within architecture. So we're taken through the history of architecture and it's given like kind of an appreciation of architecture and the way buildings shape our world, while at the same time diving into the hard maths of structural engineering and coding and computational design. Then after my studies, I went and worked with the Bjarke Ingels Group, where I was for about 3 years. And I worked as a structural engineer in Bjarke Ingels Group, where I was participating a lot in the early stages, in these very dynamic stages where you throw around shapes and ideas, and you as a structural engineer in that environment you have to be able to react with the same speed as the architects, essentially. And then actually this November, just a few months ago, I started in a new role in the engineering or consultancy firm Rambøll in the high-rise department, where I do my best to shape the high-rises in the world, using computational design in the process. So that was a short introduction to who I am and why I'm here, I guess.
Timo, in fact, I think that introduction is there's so much of credibility and so much of weight in that. In fact, I must say, I think we all are very honored to have you here. From an architect side. Thank you very much. I really appreciate you taking the time to be here. In fact, I'm quite honored, very privileged. So I'm not going to take up too much of your time and get on to the next question. You say you are an architect-friendly structural engineer. Tell us what that's about, because that's quite a stereotype that we have, architects, engineers. Talk to me about it and make me understand this.
Yeah, I guess what you say is very right, that there is a stereotype that engineers have no clue about architecture. They just want their columns. And architects, they want everything to fly. And so you have these two stereotypes. But we also know that the projects that are being built and appreciated in the future are the buildings where things work together, like buildings that stand up and have a nice architecture. So I would say my role or my vision is to make better buildings happen. I want to be in a engineering role where I can facilitate good architecture, as well as making the building stand up, of course. But basically the main thing is making better buildings happen. And that you only do through a close relationship between architects and engineers.
So I think you're very right, Timo. In fact, without, or Okay, let me rather put it this way. I feel that the divide between structural engineering and architecture has occurred at this early point, and it's created such a rift that architecture is only seen as an art and engineering is only seen as a science, and really architecture shouldn't be that, because then you are almost devoiding it of its essence. And I think you are doing good to make that mending between that. But actually that's our main focus, and we'll get to that later.
Yeah, exactly. I think we're going to dive deeper into that topic when we get towards the end.
yeah, completely right. And so this idea that you have of what structural engineering is and architecture, it almost sort of transcends the idea or that the public perceives architects and engineers to be, and even us within our own domain. But there's something different about you as well, besides the breaking of the stereotype of saying that you're an architect-friendly structural engineer. I think it's the computational design that is this sort of bridge between the two that you've mentioned even in our prior discussions. What would you define as computational design?
Yeah, so just to take one step back to the background I've had, I used a lot of my studies basically devoted to diving deep into programming, visual programming, computational optimization. Spent half a year with a Rambøll computational design team as an intern. That was a team that was back in London some years back, where I went and worked with them for half a year using computational design in the design process. That's also what I've done in Bjarke Ingels Group for my time there, really using computational design tools to facilitate a effective design process. So if I have to kind of define computational design, that could be a long night of discussion because there are many views on it. But I think computational design is essentially, you can say, it's programming, it's automation of tasks, but it's very much focused on design. So you can say it's an algorithmic approach to design problems. One of the most probably defining things in computational design is this parametric modeling, where you are modeling you can say, the rules of your building rather than the building itself.
I like how you put it. That's why I say you are gifted with words. The rules of the building instead of the building itself. That's true.
Yeah,
That's true.
so that whenever you change your building, whenever you make changes, you don't spend a lot of time doing the same thing over again. So computational design often allows, I think it springs from a bit of laziness, that you don't want to sit and model the same thing over and over again.
Yes, of course.
And the same thing often in structural engineering. You create a model in one piece of software, you want to analyze it somewhere else.
Yeah, exactly.
And then you have super skilled engineers and architects that are spending hours and hours on you can say rather dumb tasks, such as modeling, like clicking some more. But I think it's also important when we talk about computational design that we often see these grand goals of everything is parametric and we solve the whole world using computational design.
Yes.
But often I also find that it's parts of a workflow. Like we can take a lot of the workflows we're having now and then incorporate it in different places and optimize our workflows. But I actually, for this question, I wanted to show just some examples. This was a project I was lucky to work on when I was in Bjarke Ingels Group. So my role in this was, I was a structural engineer, working very closely with our architects in the super early stages. So you can imagine a building like this change over and over again. This beautiful roof you have here, the shape of that roof has had many, it has always been this kind of like circular catenary shape.
Yeah.
But because you all the time need to optimize floor area, height, the way it looks, like there's so many things that means you need to update this geometry over and over. Yeah. As a structural engineer, I can't do that. I can't make 10 different models because the architects change things regularly. So what we did was we set up a fully parametric model for the whole building. And you can see, for example, here we have one iteration of the model with a single click. Basically, I can generate a different variation or a third variation. And what we did with these was that we then made links to our BIM software, so to, in this case, Revit. So whenever the architects were ready to say, okay, now we lock the geometry, this is what we're going with, we could say click, and we had generated the entire geometry in Revit. We had it in our structural analysis software. So basically, we did a lot of footwork, you could say, to build this parametric model. But in the end, we could check hundreds of variations, and we could just say, let's go, when the architects gave the final go.
So Timo,
yeah,
sorry to interject there. Are you saying that you worked in conjunction with the architect instead of like me draw the plans and then send it to you, and then you're going to say, okay, this is not going to work, send it back? Like, no, you don't know what you're talking about. You don't know anything about aesthetics, nor do you know about design. Then you're like, no, I know what I'm doing. Is it to save time?
So in this case, our architects were placed in London and I was in Copenhagen.
Wow.
But I also, that was before Corona hit, that I had a chance right before the pandemic hit to actually go and sit with them for some days, side by side, where we basically, you could say, help each other out by sitting next to each other.
Wow.
So it allowed, like, being a fast responding structural engineer means that you can actually work together with the architects, because you're not boring. You don't say, well, I can have an answer for you in 3 weeks. If you make a change, right. You can have when you have a model like this, you can have an answer like immediately.
Right. I can see that, like, just from what you're showing, if I had to ask you to change some of the sizes, you do it and it reflects immediately, and we can have a much more progressive conversation towards completing the structure, as opposed to wasting time on several iterations. And
for the talk about better architecture, it is when you don't have someone limiting your flexibility to make changes, then, like, of course, your changes need to be sensible. You can't make the building fly, but it allows you to check multiple iterations. But I want to get to also another project to kind of show another project where the workflow was very different, but still we utilize the power of computational design tools. So this is a project that we actually did build. I was very lucky to be part of the first sketches of this project, and in the end also go to the Burning Man event in Nevada in the US, and help build this thing and put it up. So what it is, it's you can say a giant mirror ball. It's like 25 meters in diameter on a steel mast. So the main challenge of this was, how do you keep a thing like that from blowing away? And how do you keep it in a shape like this? So what we did was we made we modeled this, but not as just as a sphere on a stick. What we did was we used a tool called Kangaroo and K2 Engineering, where we could actually simulate the physics of this structure. So we modeled a membrane, we blew air into it, like this is an inflated ball basically. So our 3D model was an inflated ball. It was not a sphere. So that meant
so it's a simulation of that whole experience. It's not like as if it's just a sphere you model. It's almost as if it's actually that thing.
Exactly. So in that case, I could just play with the internal pressure and see how would this thing deform, how sensitive is it to wind, and that we could use to actually define what kind of pressure we would need inside. But I think the most useful thing for this model was actually for the assembly process. Because we had to get this thing up, so we could basically simulate, like, this is a simulation. This is our 3D model where we just took the air out of it. So we could simulate how the fabric would be on the ground, and how we would need to move it around. We could simulate the crane lift.
Wait, Timo, hang on, wait, can you go back there 1 second?
Yes.
So, Timo, you're telling me that on the left-hand side is a simulation and the right-hand side is a reality? Like, I know it says that there's labels, but you mean the computer or almost, it simulated, it said this is what it's going to look like, and it actually came out like that in reality?
This is the Rhino model to the left.
Okay.
So yes, yeah. It's a you can say completely normal 3D model made in Rhino, where we basically just took the air out of the balloon and put it down on its side and see how does it look like.
Sure. It's like you created a little microcosm of reality inside your computer.
Yes, and it proved so useful because we actually managed to discover some challenges very early on. There were plenty of challenges out there, don't worry. Okay. But using these tools was essential in getting this project to happen.
Right.
It would not have happened if, I don't believe that we could have done it without these simulations.
Okay.
Another example was the crane lift, where you could kind of simulate how will the fabric move on this mast. You can see here's one thing I didn't anticipate. There's actually a little thing on the mast here I didn't include in my model. So that was one of the challenges that came out there. Luckily we had solved it. But and the last thing is here's the same model, exactly same 3D model, but here we just applied an internal pressure, and then that's how it basically ended up looking.
Timo, that's amazing, because it's like now that you can foresee a lot of problems, as you said, before it actually happens, especially in the construction side. It's like you can almost preempt so many things. It would save time, it would save money, it would save a lot of heartache as well, because I would imagine that if you had not foreseen something on your side, it would cause quite a bit of misery to you and cause you to find a difficult time in how to process and deal with your emotions about your design as well at the same time.
Yeah. But I think there's also something we talked about the other day with this project actually being, it's an architecture piece, which at the same time is 100% an engineering project. Like the two are inseparable, and they are fused together using computational design tools to help inform the entire design process, the erection process. Everything is facilitated through the use of computational design. So I think those are two, they're very different projects, very different methods, but both show the use of computational design in helping architects and engineers working closer together and making cool projects happen.
Because that's one of the skepticisms as well, as you mentioned. People are like, why should we go with computational design or any of those, or why should we be embracing technology? We've done it all these years before, and things like that. Architecture here, as you're saying, you can see it as a placemaking tool as well as a structural engineering innovation. That's what you have here, something that's quite novel, in fact, something that hasn't been done to the scale before. But the thing that I always try to talk about and what I always discuss with students and other people is why hasn't the architectural and engineering and construction industry taken up these things quicker? Because you're saying you're doing it now, but really it's not a large scale thing. There's very few people actually doing it in terms of the mass market. So
yes.
So I think perhaps the question is then, why do you think the AEC industry is so slow to catch up?
I would say one positive thing about the AEC industry is that they are adopting. Like we see how BIM, for example, came years ago and has been widely adopted across the industry. So it shows that the industry can adopt. I think that's very positive, but it is an incredibly slow industry. And I think the reason for that being that there is a very high risk doing something new in a lot of projects. A lot of companies, they know how to design buildings in a certain way. As soon as you try new things out, you impose a risk. Yeah. And I think it's a very risk-averse industry. But I heard a very good quote from a colleague of mine the other day. I was like, we need to learn how to utilize the power of our computers before the tech companies learn to design buildings.
That's true. That's quite an insight, actually, Timo. That's actually an excellent insight, and I honestly never thought about it that way either. Wow, that's actually kind of a little bit scary, in fact. But you're right.
Yeah, but no, like we need to be able to use the technology we have at our hands, and that means that you can't have highly skilled people sitting doing work that you could hire anyone to do. Yeah. Such as clicking around in a 3D model for days and days.
True. True. I think in what you're saying there, I think the efficiency perhaps maybe outweighs the risk in many cases.
Yes, I fully agree.
So in talking about that and this efficiency, in Mario Karpo's book, The Second Digital Turn, he mentions the groundbreaking work that's done at Saket University, which is quite known for its automation and its progressive ideas towards architecture. So talking about us also being slow to catch on to it, do you think maybe the reason why there's also a bit of a resistance is because the role of architects and structural engineers might dissipate over time if they adopt these new technologies? Do you think maybe that's why?
I really don't think that our jobs per se is in danger.
That's a very progressive approach. That's like no one really says that generally. They're like, no, the machines are taking our jobs. Well, in the mainstream media, actually.
Because I would say that as it is right now, architecture is a highly human field and highly creative field. It's humans building places for humans.
Yeah.
Engineering is, like, as dull as it may seem from sometimes an architectural perspective, it's a highly creative business where you have to find solutions that best solve your problem. And the more you get to work with computers, the deeper you get into very advanced scripts and stuff, the more you realize that computers are pretty stupid. So what I normally say when people want to say, can't we just get the computer to solve this problem? Yeah. Like, we can get the computer to solve this problem when you can explain the problem to the computer. And the computer is incredibly stupid, so it needs it like told in a very stupid way. So I still think that architecture and engineering are very human arts, and I think we are very far from having computers taking over the cool part of our job. Maybe there are some things like that you get some architects and engineers to actually spend more time designing buildings and less time, again, clicking around.
No, Timo, I think that's such a valuable insight, because I think perhaps inherently in us there is a fear we feel threatened by something that's been portrayed to us. It's not necessarily that it's just an internal reaction, but really if you watch things like Terminator and some sort of technologically Armageddon sort of movies, lost some of the words there, but everyone thinks the machines are going to take over, and then you're going to have someone coming from the future to try and save you, and then mankind's dead. But you mentioned it's so human. You mentioned that we need people. Now, what would you say, in your experience, is a pathway to becoming a computational designer, since we need people to do this?
And I will start my answer with saying that I actually think computational design, including, you say, automation, programming, parametric modeling, whatever it includes, is in itself very uninteresting. It is because like it's a tool. It's the same as a hammer in itself. Is pretty uninteresting. But if you have a nail to put in the wall, it's a lot better to use a hammer than to use your hand. So I would say the computational design is only interesting in relation to our profession. So for me, I'm a structural engineer. That's my main profession. computational design in itself is, so you could what you can call it, an addition to that. Architects have their creative field as architects, but can use computational design to do that better. So I think the pathway to get there is, like to get to utilize these tools, is very much to develop an algorithmic mindset. And I know that's easier said than done. But when you sit with tasks, whatever, is it an Excel sheet, is it a modeling task, as soon as you've clicked the same button several times, that's where you should start asking yourself, could this maybe be automated? Because as soon as you get that curiosity for not doing the same thing over and over again, that's when you start automatically seeking solutions for automation. So I would say, to be a bit more direct, pragmatic about it, what I would probably do is I would download a trial of Rhino, and I would go online and watch a lot of YouTube videos and try to learn some very basics of Rhino and Grasshopper, because if you're working with 3D models, 3D data, anything that is related to our space, any data related to our 3D space, then you will have a great use in those tools.
Timo,
but the main thing is the mindset.
Yes, I think you've given such an all-encompassing answer, because you answer the kind of attitude you need to have towards it, as well as the practical nature. Because like you say, I think it's perhaps embedded in nature of people at this point in time that I'm going to download a course, I'm going to try it, maybe I won't finish it, but let me at least be somewhat exposed to it. Maybe I will never use it, but at least let me know what's going on. I think it's in the nature of people, like we do it for a lot of things. And this should be just one of those things that we should all have perhaps as a basic skill set. It's that attitude really, though, that I think that I would take, because this computational mode of thinking and an approach, and I think that that paradigm of the world has been given birth to since a long time. In fact, really, if I look back, it seems as though the discrete mathematics and mathematics as the art of logic, yes, no, almost like a Boolean kind of thinking, for the oversimplification of matters. It's this logic and critical thinking is the birth of the computing system. And so it's not really so much that as if it's something that's now. Really, the mathematics and the thinking's been there for a long time.
Yes, I agree. So I think that the main point in this is that I don't think any of us should accept from ourselves that we sit and do the same thing over and over and over again if we could actually automate it. If we could suddenly spend less time, like if you're sitting doing something boring for hours and hours that you could automate, you make your own workday better. You make your boss happy. You make better design in the end because you have time to focus on the design. It's literally, it's a win-win-win for everyone involved.
That's so true. In fact, one of the things that honestly myself I hate doing is schedules, doing window and door schedules. Like I've got to go and adjust door sizes, and if it's one in the building and it's not on a BIM system, if it's on a CAD drawing and there's 1,000 in there, I must go and look at every 1,000, and that's really honestly my time as a human being now who has intellect and has a family and has a life. I think I would do a lot better spending it on them as opposed to changing lines, and I completely agree with you.
Very much so.
So taking from what you said, computational design does seem daunting to people, but I think you've given a very real practical approach that it's an attitude towards, and it's, I think, perhaps a revision of my previous comment that I made. It's more like an attitude towards being efficient and not being, sometimes perhaps it could be born out of laziness, but really to be efficient so that you spend your time better. Somewhere else. Maybe not even efficiency. It could even be more as a prioritizing of time. Maybe that's what it gives birth to. So you can focus on other things in your life. But how do you think we could achieve these notions of becoming more, say, aware of our time? Besides what you mentioned, what do you think an architect and a structural engineer's attitude should be towards it? How could we identify this easily, and how can we adopt these in our lives?
I think it can sometimes be a bit intimidating for people when they, for example, see like the two projects that I just showed earlier.
Yeah, those are massive ones. Sure.
Yeah, and you see, okay, some crazy physics simulation and a fully parametric model that are never going to learn can very easily be.
Yes, you're quite right.
Be the attitude, and what I see both on like different media, different forums, when you see people advertising computational design, it is often done through these prime examples, the cool things you want to show.
Yeah.
But I think that even as a non-expert, someone who has never touched, for example, Rhino Grasshopper before, you can, with very little training, create immense value for your own work. A good example that I like to bring up is I did an architecture course at one point in Singapore.
Okay.
Where I was making a design where it ended up being literally stairs everywhere. And I got so annoyed at modeling stairs that I had to think there has to be a better way so I don't have to sit and adjust this stair geometry.
Yeah, true.
So just like a very, very simple script to make automatic stairs that follow a line in your model. Then you don't, like, I saved hours on just having a script that took maybe 10 minutes to make.
Oh, now there, that's efficiency. Oh.
And actually I was thinking also in between our two chats here that I'm actually having in the making on my LinkedIn. I'm going to post a little series of you can say simple examples of creating value using Grasshopper and Rhino, because I think very often you see the very fancy examples. You think you cannot get any value yourself if you're not an expert. But what I really want to show is that with a few hours of training, you can get to a point where you can already there create a lot of value.
Now that's value. That's value.
And a last comment I want to add to that is that 90% of the computational design work I do, or when I use these tools, is for very simple things. That could be just visualizing some Excel data in my 3D model. Then I can put that into Grasshopper, quickly visualize it. Little scripts that don't take more than 5 minutes to make. So I think that's important to have that in mind, that it doesn't need to be large, intimidating. There's a value in small things.
I think that's very valuable, especially to students, because if there's a student coming on board and they see this stuff, they're like, you'd naturally be intimidated. You'd naturally think, well, sure, how will I ever be able to achieve this? And then you start seeing that it's not really just about the big projects that seem complex and seem with these organic shapes that are crazy, or even parametric parametric shapes. Really, you start seeing that, like you just said, it's in the things you can do every day. There's more value than just creating form. It's value in productivity and workflow.
I would like to know what bigger percentage of architecture students who have been doing all-nighters, sitting at 3 o'clock at night, clicking on stupid facade elements or something like, oh, I only have 500 to go. I'm probably done at 7 o'clock in the morning.
Very true. Very, very true. If I had my emoji thing here, I would have sent a little blue clap on the screen and like, yes, exactly. Well done. Very, very true. And I think we should do that, Paul. In fact, I think probably we'll do it afterwards. But so just moving to the next question, which I think is really the heart of the whole conversation. And I think this is where I find you so interesting. Is the response that you, or the attitude you have towards this question. And that question is, do you think that computational design could be the bridge where architecture and structural engineering meet? Do you think this is what can unite that divide created so long ago?
And that is a very difficult question, but I would start to say that, of course, you can have this maybe slightly utopian idea that you can bring together structural engineering and architecture using a single tool. And that I think that is not what you can do. But I think the main bridge between architecture and engineering is a mutual understanding of each other's needs. That you as an engineer understand that there is something called functionality, aesthetics, and that you are not an expert in those fields, and that the architect's opinion is very valid. And as an architect, you need to understand that structure is required, and if your building is not living up to the requirements, it's going to get very expensive and maybe not be built. But I think what it allows is that it allows us to walk into each other's playing fields. Because in the design process is that architects are very fluid in the design process. You can generate very many iterations in a short amount of time, check different variations.
Yeah, true.
Engineering often needs a finalized product. And then when we have this finalized product, we start looking at the columns, at the slabs, at different things. And then we set up a fancy model. And then after some weeks, we have looked through things and we come to the architects and say, this solution or this proposal you sent us 3 weeks ago, there are some things we want to change. And by that time, that proposal doesn't even exist anymore.
Yeah.
It's
a whole 1,000 other iterations down. Yes, it's a new building completely.
So the design process has often led to this situation where architects actually prefer to have the engineers involved when the design is done.
Yeah. Because
the engineers can't follow their speed. Yeah. So I think what computational design makes possible is that it makes possible that I, as an engineer, can very quickly compare architectural solutions because I have tools to quickly transform the architectural idea to a structural idea. Yeah. Often I also don't need to know the details of my, does this column need to be 500 mil or does it need to be 600? We don't really care. Well, what I care about in the early stages are on a much more higher level, is there a column or is there no column?
Yes, exactly.
So I think, at least what I experienced is, in my last years in Bjarke Ingels Group, that these projects where I've had a possibility to really be deep in the design process, there have been so much fun for both architects and engineers because we talk the same language. The architects come with a funky design. I test it immediately and I can send them a response the same day saying, it looks like this solution would require about 20% more material. Is it really that good? And then they might say, maybe that's too much. So I would say it allows engineers to have speed. The danger for engineers is then that it also allows architects to work even faster.
Very valid concern.
And just an example of that, how you could say computational design can also help. What can you say? No, I actually want to talk. I want to save that example for later.
Okay.
Let's talk about that later. It doesn't fit in so well here.
Okay. Well, I actually just want to make a comment on what you said as well, because I honestly find it very insightful to see that this thing that we've created, this computer, this machine that we have given birth to almost, is a thing that helps us unite in a way and find out more about ourselves than we wouldn't have done otherwise. It's quite interesting, the idea that this machine is a thing that could possibly assist architects and engineers in coming together. And there's always been this sort of idea that, the machine is something that belongs in its own realm. But once it's integrated into our work, I think we begin to understand more about ourselves.
Yes.
and more about the perception in future, or more about rather the perception of the future can be like. So
I very much agree.
I think that everything that you mentioned now was quite insightful into an approach towards computational design. And it's also quite insightful as to how, okay, I'll just give you an example quickly. I was working on a university building, and one of the things that we did in the university building was, again, door schedules and floor plan layouts. And what had happened by the time we actually completed the various iterations we'd done and we sent to the engineer and the quantity surveyor, the entire design had changed to such an extent that they had to now revisit another 5 iterations of our own. And coming back, when they finally got the 5 we'd done, we were already on number 10. And like you're saying, that's just ridiculous. It just wastes too much of time. It's absolutely ridiculous. It also costs a lot of money as well. It's a large project. The budgets start running overboard. You push the deadlines forward. And I think if we had worked with that at the time, a lot of those issues could have been mitigated. Again, even as well, things like old emails that were sent and old files. If you're not working with the same file at the same time, you're going to have lots of different versions. And that was a problem that we experienced. Yeah.
But I think to add to examples like this building I showed in the slides earlier,
yeah,
where we made a parametric model basically for everything in the building. Everything has.
Hello, Timo, you there?
They actually adopted quite a few parts of our model. Like we developed the parametric model among us engineers and shared it with the architect, and they took parts of the model that they liked. So suddenly also their design process could be like they could check all these different solutions so much quicker because this roof geometry was very complex to model otherwise.
Right.
So when they were suddenly told we need to have 10,000 square meters more, how can we get that? Then you just change this little parameter, and then they had 10,000 square meters more. Use the value here of 21.5. Then I would put the same value into my model, and I would have the geometry. Like it would take a few minutes to then make an update.
Sure, that's quite an exciting example that you mentioned, and I think there's so much of benefits to it. I think we'd be able to go on for quite a while, because really, I think if people heard of these little stories or these little successes, I think it might be easier adopted into the workflow. In fact, then people will be going more towards direction. In fact, even then, architectural education in itself should start adopting more of these methods. Actually, and it's a little bit off topic, but the education that you received seemed to have been quite directed in this way. Would you say you yourself as an individual is entirely the reason for your interest in computational design, or would you say that the course somewhat supplemented that?
I would say that the course very much supplemented that, but it was also, well, it's a good question actually, because at that time in university there was actually not really any courses to facilitate the learning.
Okay.
So there was a general interest among some of my co-students, but I had the possibility to have an internship where I learned a lot and could then take programming classes in our compute department. But what I have also often found is that when you meet someone who is really good in computational design, it is often something that they learned on the side, because
yes, true.
You don't have very many universities who offer much much support, any courses or anything to learn it. So it's very often people who just thought, hey, this looks amazing, I need to learn this.
Yeah.
It's seen as a style, possibility.
But it's seen as a style more than an attitude towards it. You're quite right.
Yes.
In fact, the latest one I've seen really, and the only one that I've seen currently that has some gravitas to it, seems to be the data science for the AEC industry. And that's, I think, by Harvard. That's the only one I've seen really.
Yeah.
That somewhat incorporates this idea towards taking computational design, the information we have, and actually using it. And it's not even architectural. It's really just taking information and doing something with it.
I know that there are in the Royal Academy of Arts, they have what they call like a a studio where they work a lot with computational design tools. Okay. At Chalmers University in Sweden, they also have quite a bit. Like, it's getting more and more, which is really good to see.
But I really usually only see it on a postgraduate level, never at an undergraduate level.
No, that is true. That is true.
So I think perhaps there should be a bit more of a drive, even towards especially countries with an economy that needs some injection in terms of infrastructure. I think computational design would definitely assist with the efficiency of such infrastructure being built. Like
yes, no, I agree. Also because it allows you to speed up processes as well. Whenever you design something where you have a lot of repetitive work, you no longer need to just throw man hours at it.
Yeah.
It's not that you solve a repetitive task by spending more time on it.
Yeah.
You have to solve it smarter. And with a new generation of students who are getting more and more you can say aware of these tools, I think we're going a good time. Have a good time ahead when it comes to that.
So talking about ahead, my final question to you on this would be, in your opinion, what do you think the future of architecture holds in store? And how do you think this can be achieved?
When we talk about architecture, I want to kind of divide it into two types of architecture.
Okay.
Because there's one type which is like opera houses and big theaters, and you can say the landmark architecture.
Yes.
Which is one thing. But then there is the 99% of buildings that are being built which are not opera houses.
Yeah.
Which often have different budgets, which are what is the mass of our cities, is that kind of architecture. And I think that's what most of us are going to work with anyway.
True.
And what we're going to live in. So that's kind of what I want to talk about. And I think that in the future, and already now, we see the environmental impact of our buildings having a greater and greater importance in the way we design. We can no longer ignore the impact our buildings have. So we start to be more and more data-driven in our design. We can no longer accept that we just put a glass facade towards, in Northern Europe, it's towards the south, it's probably towards North and South Africa.
In South Africa, that's right.
Right. But where that is just not acceptable for future architecture.
No.
But it also puts some requirements to us as engineers and architects, because we suddenly have much more data that we need to include in our designs.
Yeah.
And that puts a natural responsibility on us to be able to use that data. And I think a good example is actually, now some architects that I have a pleasure of working with now. It's Henning Larsen Architects. It's a Copenhagen-based architecture firm who are very well known for, they're designing buildings based on the data that is available. So what is the sunlight like? What is how's the wind comfort? Where do we source our materials from?
Right.
All these things. And you cannot use that data efficiently if you don't know how to harness it and how to use it. So we need to use these digital tools to harvest that. So in our design process, the need for engineers will be bigger, because we need to have that all this knowledge included in our designs. That means that we are forced to work closer together, because we have such a responsibility. So to ask your question about what I think the future of architecture holds, I think it holds a greater relationship between architects and engineers, because our goals are much more aligned now towards making buildings that are actually better, and not just looking nicer or having columns of the right size. We want to minimize the impact of our buildings, and that requires architects and engineers to work close together. And that's where computational design is a tool that can help facilitate that.
Yeah, I think you're quite right, Timo, because it's one of the many facets which we can use towards getting ourselves in a space where we begin to now start to re-ask, okay, then what really is architecture? What can it do instead of just be a place of shelter, or instead of just being a placemaking tool? Perhaps it can be more subservient towards the environment, more subservient towards the community, and more subservient towards perhaps society, like people as a whole. Whether it's our well-being, the ventilation of spaces, or whether it's the amount of resources that we use. Perhaps our buildings could monitor monitor our consumption of water and electricity and report back to us, and we can interact with this information. Maybe our buildings aren't just static anymore. Maybe they can be a tool for us to communicate with. It's almost as if it's a reflection of our lifestyle, and that we can see and use and do something with.
Yeah. Well, but also the fact that you say governments around the world are also, of course, getting more and more aware of the responsibility that we have towards our planet. So, for example, in Denmark, as an example, we have had, like, pretty much every 5 years so far, the regulations have become stricter and stricter to like what kind of energy usage your building can have, what kind of footprint it can have. So you can no longer just sit down and make a fancy sketch and say, this is my project, because then they'll come and say, well, it doesn't satisfy any criteria.
Right.
And how do you then make beautiful architecture that still satisfies those criteria? You need to know how you satisfy those criteria. And again, that requires a close cooperation between experts in all fields.
Yeah, in fact, Timo, I think it sounds like you're saying that we have all these requirements and all these constraints and all these parameters. And that sounds like computational design, eh? That sounds like a computational design task on its own. So Timo, thank you very much for attending. What insights you brought into this conversation, because making this kind of information accessible to people is I believe, the key towards us making a progressive change. It's also key towards informing the public, because people are more aware now than they ever were before about life in general. You can research so much of information, and this kind of information begets more knowledgeable people, more informed people who make better choices towards the well-being of themselves and society.
But also just to give a little note about what I see happening right now.
Yes, please.
For example, like now I have been hired into Rambøll.
Yes, right.
And in the high-rise team, which is in many ways a very like a conventional way of doing engineering, but there I really see a desire to get these methods implemented. It's no longer a nice to have. It's a need to have.
That's it. Yes, that's it. You need to have. You're right. Completely right, Timo. Sorry, I had to interject.
That was also like, that is one of the things that I'm working very much on right now, is that within the company try to spread the knowledge and the awareness of what these tools can bring. I think the industry in general is not on a very high level yet.
Yeah.
So if you are a young engineer architect coming out, having those skills, you are going to be very valuable for companies.
Yeah, I think undoubtedly. And Timo, I think that the work you're doing plays a very important role. And I think everyone in the audience could have taken something away today that can contribute to this forward-moving progress that we have. Because we're at a time now where technology can aid us in ways that are unprecedented. The rapid spread of information is quite significant. In fact, we could get a message across much faster, and that's how things like a lot of political movements and a lot of social movements could be made, because we have the technology to facilitate our desire to make great changes. In fact, the technology to some degree complements our inherent want to make things better. And everyone that's here, we have reached the 1 hour mark. And I think Timo and myself could go on for hours about this and on and on and on, because it is something that unfortunately isn't spoken about in a manner that it seems very possible to do. It almost seems as if it's either, like Timo said, it's a nice to have, or it's excessive. So we're just going to cut it at or this meeting at this point in the discussion, and we're actually going to take some questions.